Welcome back to my channel. In this tutorial video, we'll discuss one of the fundamental concepts in thermodynamics, that is thermoequilibrium. What is thermoequilibrium? Thermoequilibrium happens when two objects at different temperatures come into contact and eventually they reach the same temperature. This is because heat will flow from the hotter object to the cooler one. That simply means the heat lost by the hotter object is equal to the heat gained by the cooler object, which is Q lost, that is heat lost, is equal to the heat that is gained, Now let us look at the problem where objects at different temperatures are brought in contact and eventually attain the thermoequilibrium. Here is the problem. A 200 grams copper calorimeter can contains 150 grams of oil at 20 degrees Celsius. To the oil is added 8 grams of aluminium at 300 degrees Celsius. What will be the temperature of the system after equilibrium is established? So you have to identify the objects that are involved in forming this system. So we have three things that are involved in forming this system. One, we have a copper calorimeter, we have oil, and we have aluminium. In this case, aluminium is the hotter object that is going to lose heat to copper calorimeter can and the oil. So how do we approach this problem? We know that the heat lost by aluminium will be equal to the heat gained by the copper calorimeter can and the oil. You can pause the video and write down the question and the values for the heat capacities of copper, aluminium and oil before we start answering the question, so that when we do start answering the question, we'll be on the same page. Please pause the video and take note of the question. Let us answer the question now. We know that the heat lost is equivalent to the heat gained. Aluminium is losing heat while copper and oil are gaining heat. If we add the heat lost to the heat gained, we must get 0. So the heat gained by copper plus the heat gained by oil plus the heat lost by aluminium must give us 0. So that is our equation. In this case, the question is simple because there is no change of state in our system. If there was a change of state, for example, there was freezing or melting or evaporation or condensation during the processes, then we are supposed to consider also the latent heat. Okay. For freezing, take note, for freezing or melting, the heat lost or heat gained is equal to mass times the latent heat of fusion. That is for freezing and melting. Then for evaporation and condensation, the heat gained, that is during evaporation, that is equal to mass times latent heat of fusion. And then if there is condensation, then that is the heat lost is equal to the negative m times LV, that is mass times latent heat of fusion. And then for any other process which is not the change of state, the heat gained or lost is equivalent to the heat capacity times mass times the change in temperature. So using this formula here, let us now substitute. We have the heat capacity of copper times the mass of copper times the change in temperature, that is the temperature final attained by the system, Tf, minus the initial temperature. For copper, the initial temperature is 20, plus the heat capacity of oil times the mass of oil times the change in temperature, that is T final. So you can see that the T final is same for all the three objects involved. Oil is also at 20 degrees Celsius initially, plus the heat capacity of aluminium plus the mass of times the mass of aluminium times the change in temperature of aluminium, that is Tf, but aluminium is at 300 degrees Celsius. So physics ends there. The rest is mathematics. You distribute now. So if we distribute the heat capacity of copper and mass of copper times this, we are getting that. And then this times this, we are getting this. Then the heat capacity of oil times mass of oil times Tf, we are getting that. And then times plus the heat capacity of oil times this times 20, we are getting that. So we do the same even for this part here. What do we do next after that? Next, we make Tf the subject. We correct the like terms. So we have this term having Tf, even this term here having Tf. So after that, after we correct the like terms, we can factorize Tf. So Tf is common. We factorize Tf here. So if we do that, then here we remain with heat capacity of copper times mass of copper, plus here we remain with the heat capacity of oil times mass of oil, plus here we remain with heat capacity of aluminium times mass of aluminium. And then we factorize Tf like that. Then the rest will go to the other side of the equal sign. So if this goes to the other side here, it will become positive. So that's this. And then this also goes to the other side of the equal sign. It also becomes positive. It becomes this. This also jumps to the other side of the equal sign. It also becomes this, positive. Now we can divide throughout by this. If we divide throughout by this, both on the left side and the right side, then we'll have Tf remaining on the left side. Please, you can pause the video and do the computing there. You do the calculations, you use your calculator. You can substitute the values even here, there is no problem if that's what you are good at. Okay, for me, I think it's good. I play with the equation. I make Tf the subject of the formula, then I just substitute the values at last so that I don't round off the values too much. Okay, so after we divide both sides by this here, then we have 20 times heat capacity of copper times mass of copper plus 20 times heat capacity of copper times heat capacity of oil times mass of oil plus 300 times heat capacity of aluminium plus mass of aluminium over the heat capacity of copper times mass of copper plus the heat capacity of oil times mass of oil plus the heat capacity of aluminium plus the times the mass of aluminium. You can take the mass the way they are in grams, since the heat capacity is also given in calories per gram, so it's fine like that. And then if we now substitute the values, okay, we've been given the heat capacity of copper, that is 0.093 calories per gram per degree Celsius times the mass of copper, which is 200, plus 20 times 0.3, which is the heat capacity of oil, times 150, which is the mass of oil, plus 300. Okay, we substitute for all the variables here, and then after that you can pause the video again and then use your calculator and do the calculations. After that, regardless of the calculator, the type of calculator that you are using, you should get 71.75 degrees Celsius as the final temperature of the system, which you can round off to 72 degrees Celsius as the final temperature of the system now. And that is to say the thermal equilibrium temperature is 72 degrees Celsius. So the system attained the thermal equilibrium at 72 degrees Celsius. So you've seen that initially copper and oil was at 20 degrees Celsius, while the aluminium was at 300 degrees Celsius. And finally, the combination of copper and oil and aluminium is having the temperature of 72 degrees Celsius, the same temperature for the system. So that is equilibrium, and that's how we answer problems that involves thermal equilibrium in thermodynamics. Thank you for watching. If you haven't subscribed to my channel, please subscribe to my channel. Leave me a comment you like the video. You also invite others to follow my YouTube channel and subscribe, so that every time I post a new video, you will get the notification and will be on the same page. You will always be updated. Thank you for watching once again. See you in the next video.